Let's analyze this cubic polynomial and find its factored form and where it's negative. Here we have a cubic function that crosses the x-axis at 3 points. To find the factored form, we'll use these x-intercepts as our roots. The roots are -1/3, 1, and 5/2. These will be our factors. Therefore, our function must have the form f of x equals k times the factor x plus 1/3 times x minus 1 times x minus 5/2, where k is some constant we need to find. To write this with integer coefficients, we'll multiply the first factor by 3 and the last factor by 2. This gives us f of x equals k times 3x plus 1 times x minus 1 times 2x minus 5. To find k, we can use the y-intercept. From the graph, we can see that f of 0 equals -15. Let's substitute x equals 0. Therefore, our final factored form is f of x equals -3 times 3x plus 1 times x minus 1 times 2x minus 5. Now for part B, we need to find where f of x is less than 0. Looking at our graph, we can see that the function is negative between -1/3 and 1, and also from 5/2 onwards to infinity. We can write this in interval notation as x is in the interval from -1/3 to 1, union with the interval from 5/2 to infinity. And that completes our analysis of this cubic polynomial. We've found its factored form with integer coefficients and determined where it's negative. Let's analyze the trigonometric function g of x equals 5 sine of 3x over 4 minus 2. We'll find its amplitude, period, and sketch its graph. Let's break this down step by step. First, let's find the amplitude. The amplitude of a sine function is the absolute value of the coefficient in front of sine. In this case, that's 5. This means the function will oscillate 5 units above and below its center line. Next, let's find the period. For a sine function, the period is 360 degrees divided by the coefficient of x inside the sine. Here we have 3x over 4, so our period is 360 degrees divided by 3/4, which equals 480 degrees. Now, let's sketch the graph. We'll create a coordinate system from -180 degrees to +180 degrees. First, let's note that the -2 in our function shifts the entire graph down 2 units, so our center line will be at y equals -2. Let's plot our function. The graph will oscillate 5 units above and below the center line at y equals -2. This means our maximum value will be at y equals 3, and our minimum value will be at y equals -7. Let's highlight some key points. Since our period is 480 degrees, and we're only showing from -180 to +180 degrees, we won't see a complete cycle. However, we can see that the function maintains its amplitude of 5 units and stays centered around y equals -2 throughout the domain. In summary, we found that this function has an amplitude of 5, a period of 480 degrees, and is shifted down 2 units from the standard sine function. These 3 characteristics completely define how our function behaves. Let's solve this problem step by step. We're given that when ln of y plus 2 is plotted against x squared, we get a straight line that passes through 2 points. Let's first plot these points on a coordinate system. Here's our x squared axis horizontally and ln of y plus 2 axis vertically. And here are our 2 points, 2.25, 9.37, and for 0.75, 3.92. Since this is a straight line, we can use the point slope formula. The slope m equals y2 minus y1 over x2 minus x1. That's 3.9. 2 minus 9.37 divided by 4.75 squared minus 2.25 squared. Now that we have the slope, we can use the point slope form of a line, y minus y1 equals m times x minus x1, to find the equation. Using the first point and our calculated slope of -2.18, plugging in the point 2.25, 9.37, we get 9.37 equals negative 2.18 times 2.25 squared plus c. Solving for c gives us 14.275. Now we have our complete equation. ln of y plus 2 equals negative 2.18x squared plus 14.275. To solve for y, we need to use the exponential function, taking e to the power of both sides. Y plus 2 equals e to the power of negative 2.18x squared plus 14.275. Finally, subtracting 2 from both sides gives us our answer. Y equals e to the power of negative 2.18x squared plus 14.275 minus 2. And there we have it. We've found y in terms of x by using the fact that ln of y plus 2 forms a linear relationship with x squared. Let's solve this binomial expansion problem step by step. First, let's look at part A. We need to find the values of n, p, and q in the expansion of 1 minus x over 2 to the power n, where the first 4 terms are given as 1 minus 8x plus px squared plus qx cubed. Let's use the binomial theorem to expand this. The general term in the expansion will be the sum from k equals 0 to n of n choose k times negative x over 2 to the power k. Let's write out the first 4 terms. The first term is when k equals 0, which gives us 1. The second term, when k equals 1, gives us negative nx over 2. The third term gives us n 1 over 8x squared. And the fourth term gives us negative n 1 n2 over 48x cubed. Now we can compare coefficients. From the x term, we get that negative n over 2 equals negative 8. So n must be 16. Using n equals 16, we can find p from the x squared term. This gives us p equals 30. And finally, we can find q from the x cubed term, giving us q equals negative 70. Now, let's solve part B. We need to find the term independent of x in the expansion of 2 over x squared plus x over 3 to the 6th power. Let's write out the general term using the binomial theorem. The general term will be 6 choose k times 2 over x squared to the power 6k times x over 3 to the power k. Simplifying this, we get 6 choose k times 2 to the power 6k times x to the power k minus 12 over 3 to the power k. For the term to be independent of x, the power of x must be 0. So k minus 12 equals 0, meaning k equals 4. Substituting k equals 6 back into our expression and simplifying, we get 6 choose 6 times 2 to the 0 power over 3 to the 6th power, which equals 20 over 27. Therefore, the term independent of x in the expansion is 20 over 27. Let's solve this trigonometric equation step by step. We need to solve 3 secant squared of 2 theta plus pi over 6 equals 4, where theta is between negative pi over 2 and pi over 2. First, let's isolate the secant squared term by dividing both sides by 3. This gives us secant squared of 2 theta plus pi over 6 equals 4/3. Next, recall that secant squared equals 1 over cosine squared. So we can rewrite this as 1 over cosine squared of 2 theta plus pi over 6 equals 4/3. Multiplying both sides by cosine squared and simplifying, we get cosine squared equals 3/4. Now, let's take the square root of both sides. Remember, when we take the square root, we get both positive and negative values. So cosine of 2 theta plus pi over 6 equals plus or minus square root of 3 over 2. Let's visualize this on the unit circle. The cosine value of square root of 3 over 2 occurs at angle pi over 6 or 30 degrees, and negative square root of 3 over 2 occurs at 5 pi over 6 or 150 degrees. Now we can solve for theta. From the positive case, we get 2 theta plus pi over 6 equals plus or minus pi over 6. And from the negative case, we get 2 theta plus pi over 6 equals 5 pi over 6 or negative 5 pi over 6. Solving these equations and considering our domain restriction, we get 3 solutions: negative pi over 6, 0, and pi over 3. To verify these are correct, we can plug each value back into our original equation. Each solution satisfies our equation and falls within the required domain of theta between negative pi over 2 and pi over 2. Let's solve this polynomial problem step by step. We have a polynomial p of x equals a x cubed plus bx squared plus cx minus 5, where a, b, and c are integers. We're given three important pieces of information. First, the derivative of p at x equals 0 is 12. Second, 3x minus 1 is a factor of p of x. And third, when p of x is divided by x minus 2, the remainder is 95. Let's start with the derivative condition. The derivative of p of x is 3x squared plus 2bx plus c. When we evaluate this at x equals 0, we get c equals 12. Next, let's use the remainder theorem. When x equals 2, p of 2 equals 95. This gives us the equation 8a plus 4b plus 24 minus 5 equals 95. Simplifying, we get 2a plus b equals 19. This is our first equation. Now for the factor condition. Since 3x minus 1 is a factor, p of 1/3 must equal 0. When we substitute x equals 1/3 and c equals 12, we get a plus 3b equals 27. This is our second equation. Let's solve these equations simultaneously. Multiplying equation 1 by 3 and subtracting equation 2, we get 5a equals 30, so equals 6. Substituting back, we find b equals 7. Therefore, we have found that a equals 6, b equals 7, and c equals 12. Now for part b. To show p of x equals 0 has only one real root. Let's look at the derivative of p of x, which is 18x squared plus 14x plus 12. The discriminant of this quadratic is negative, meaning p prime of x has no real roots. Therefore, p of x is strictly increasing. And since we know 3x minus 1 is a factor, p of x can only cross the x-axis once, meaning it has exactly one real root. In conclusion, we found the values of b and c and proved that the equation has exactly one real root at x equals 1/3. Let's solve this combinatorics problem step by step. We'll start with part A, which deals with forming 6-digit numbers. For part AI, we need to find how many 6-digit numbers can be formed using the digits 0 through 9, where each digit can only be used once, and the number cannot start with 0. Let's break this down. For the first digit, we can use any number except 0, so we have 9 choices. For the second position, we have 9 remaining digits to choose from. For the third position, 8 digits. For the fourth, 7 digits. For the fifth, 6 digits. And finally, for the last position, 5 digits. Using the multiplication principle, we multiply all these choices together. That's 9 times 9p5, which equals 9 times 15,120, giving us 136,080 possible numbers. For part AI, we need to find how many of these numbers are divisible by 5. A number is divisible by 5 if, and only if its last digit is either 0 or 5. Let's solve this case by case. Case 1. When the last digit is 0, we have 9 choices for the first digit, not 0, and we need to arrange for digits from the remaining 8 digits. Case 2. When the last digit is 5. We have 8 choices for the first digit, not 0 or 5, and we need to arrange for digits from the remaining 8 digits. Adding these cases together, we get 28,560 numbers that are divisible by 5. Now let's move to part B, which involves selecting a committee. We have 6 doctors, 10 nurses, and 8 dentists, and need to select 7 people total. For part BI, the total number of possible committees is simply choosing 7 people from 24 total people. That's 24 choose 7, which equals 346,104 committees. For part BI, if all doctors must be on the committee, we first include all 6 doctors, then we only need to select one more person from the remaining 18 people. That's 18 choose 1, which equals 18 possible committees. Finally, for part B3, to find committees with at least one dentist, we can subtract the number of committees with no dentists from the total number of committees. This gives us 346,104 minus 11,440, which equals 334,664 committees. Their inverses. We're given that f of x equals 3x plus 1 squared minus 4, and we need to find the least possible value of a such that f inverse exists. For a function to have an inverse, it must be either strictly increasing or strictly decreasing. Let's find the derivative of f of x to determine where the function is increasing or decreasing. The derivative is 6 times 3x plus 1, setting this equal to 0. 6 times 3x plus 1 equals 0. Solving for x, we get x equals negative 1/3. This is the critical point of our function. Let's visualize this with a graph. Here's our coordinate system. The function is a parabola that opens upward, with its vertex at x equals negative 1/3. The function reaches its minimum value at this point. Since the function is strictly increasing for all x greater than negative 1/3, this must be our value of a. Therefore, the least possible value of a is negative 1/3. For part 2, we need to find the range of f. Since the function has a minimum value of negative 4 at x equals negative 1/3, and increases without bound after that, the range of f is all values greater than or equal to negative 4. Now, for part 3, let's sketch both f of x and f inverse of x. Remember, f inverse is the reflection of f across the line, y equals x. The blue curve shows f of x, and the red curve shows f inverse of x. Notice how they're reflections of each other across the yellow line, y equals x. The y-intercept of f of x is negative 3, and there are no x-intercepts. Let's solve this complex equation involving fractional exponents. We need to solve 12x to the 2/3 minus 5x to the negative 2/3 minus 11 equals 0 for x greater than 0. The first step to solving this equation is to make a substitution to simplify it. Let's let y equal x to the 1/3 power. This means that x equals y cubed. Using this substitution, our equation becomes 12y squared minus 5y to the negative 2 minus 11 equals 0. To eliminate the negative exponent, let's multiply every term by y squared. This gives us 12, y to the 4th minus 11y squared minus 5 equals 0. Now, we can make another substitution to turn this into a quadratic equation. Let's let z equal y squared. This transforms our equation into 12z squared minus 11z minus 5 equals 0. We can solve this using the quadratic formula. The quadratic formula states that z equals negative b plus or minus the square root of b squared minus 4ac, all divided by 2a. Here, is 12b is negative 11 and c is negative 5. Let's substitute these values into the quadratic formula. This gives us z equals 11 plus or minus the square root of 121 plus 240 all over 24. Simplifying under the square root, we get z equals 11 plus or minus 19 over 24. This gives us z equals 30 over 24, or negative 8 over 24. Since we know that z equals y squared, z must be positive, so we can discard the negative solution. Remember that z equals y squared, so y equals plus or minus the square root of 5 over 2. Since x equals y cubed, x equals the cube of the square root of 5 over 2. Finally, when we calculate this value and round to one decimal place, we get x equals 1.4. You can verify this solution by plugging it back into the original equation. Let's analyze a curve given by the equation, y equals the square root of 5x minus 2 divided by x minus 3. We'll explore why this curve doesn't exist for certain x values and find its derivative. Let's start with part A, explaining why the curve does not exist when x is less than 2/5. Let's visualize this by graphing the curve. For a curve involving a square root, we need to consider the domain, where the expression under the square root is non-negative. In this case, we have square root of 5x minus 2. This means 5x minus 2 must be greater than or equal to 0. Solving this inequality, 5x is greater than or equal to 2, therefore x is greater than or equal to 2/5. Here's the point x equals 2/5 on our graph. The curve only exists to the right of this point. Now for part B, we need to find the derivative dy dx and show it can be written in a specific form. Since our function is a quotient, we'll use the quotient rule. Let's identify u and v. U equals square root of 5x minus 2 and v equals x minus 3. Now we need to find du dx and dv dx. The derivative of u requires the chain rule. The derivative of square root of 5x minus 2 is 1 over 2 times the square root of 5x minus 2 times 5, and dv dx is simply 1. Plugging these into the quotient rule, we get this expression. After simplifying the numerator, we get negative 5x plus 11 over 2 times x minus 3 squared times square root of 5x minus 2. Therefore, comparing with the given form, we can see that a equals 5 and b equals 11, which are both positive integers.